The face-centered cubic lattice contains 8 atoms at the 8 corners of a cube and 6 additional atoms in the faces of the cube. Although the face-centered cubic lattice is often drawn to emphasize the cubic nature of the structure, it is also a close-packed structure. The face-centered cubic results from the stacking of close-packed layers in an ABC fashion, so that the 4th layer lies over the 1st layer, the 5th layer lies over the 2nd layer, and so on. Here we use color to represent the 3 close-packed layers in the face-centered cubic lattice. Two types of spaces or holes exist between the layers of close-packed structures. The first type of hole is called an octahedral hole and is formed between 3 atoms in one close-packed layer and 3 atoms in a second close-packed layer immediately above or below the first. The space at the center of a face-centered cubic is actually an octahedral hole and is formed by 3 atoms in the green close-packed layer and 3 atoms in the blue close-packed layer. In all subsequent discussions, we will represent octahedral holes with partially transparent polyhedra as shown here. Despite the name, it takes 6 atoms, not 8, to define an octahedron. The term octahedron is derived from the fact that such a polyhedron has 8 sides. The center octahedral hole is the only one that lies entirely inside the cell shown here. Other octahedral holes lie partially inside this cell. The center octahedral hole shares each of its 12 edges with 12 other octahedral holes. 8 of these are shown here. Each of these lies 1/4 inside the cell. Overall, an array of n atoms in a close-packed structure actually gives rise to n octahedral holes. The second type of hole that exists between the layers of close-packed structures is called a tetrahedral hole. Tetrahedral holes are formed between 3 atoms in one close-packed layer and a single atom in a second close-packed layer immediately above or below the first. As before, we will switch to transparent polyhedra to represent the tetrahedral holes in our face-centered cubic lattice. The cell shown here contains 8 tetrahedral holes at the 8 corners of the cube, and these lie entirely inside the cell. An array of n atoms in a close-packed structure gives 2n tetrahedral holes. Several different ionic lattices adopt structures in which one set of ions form a face-centered cubic array and the other set of ions occupies the octahedral or tetrahedral holes. In the following sections, we will discuss 3 ionic structures that can be described in this way. Halite is the mineral name for sodium chloride. In the halite structure, the relatively large chloride ions, represented by the green spheres, form a face-centered cubic array. The sodium ions, represented by the white spheres, occupy the octahedral holes. Each sodium ion lies at the center of an octahedron of chloride ions. Since an array of n close-packed atoms give n octahedral holes, and since there is 1 sodium ion for every 1 chloride ion, all of the octahedral holes are occupied. In contrast, the tetrahedral holes are vacant. We can gain a different perspective on this structure by examining a space-filling model. The structure is based on a face-centered cubic array of chloride ions and therefore contains close-packed layers of chloride ions. By removing successive layers, we see that the sodium ions as well as the chloride ions form close-packed layers. The structure can therefore be described as alternating close-packed layers of sodium and chloride ions. A second ionic structure that is based upon a face-centered cubic lattice is the fluoride structure. Fluoride is the mineral calcium fluoride. In the fluoride structure, the calcium ions, represented here by the white spheres, form a face-centered cubic array. The fluoride ions, represented by the green spheres, occupy the tetrahedral holes. Each fluoride ion lies at the center of a tetrahedron of calcium ions. Since an array of n close-packed ions gives 2n tetrahedral holes, and since there are 2 fluoride ions for every 1 calcium ion, all of the tetrahedral holes are filled. Last, let us examine a space-filling model of the fluoride structure. The space-filling model shows us that the array of calcium ions is greatly expanded to accommodate the fluoride ions. The primary reason for the adoption of this arrangement is stoichiometry. A third ionic structure based upon a face-centered cubic lattice is the sphalerite structure. Sphalerite is the cubic form of the mineral zinc sulfide. In the sphalerite structure, the relatively large sulfide ions, represented here by the yellow spheres, form a face-centered cubic array. The zinc ions occupy the tetrahedral holes. Each zinc ion lies at the center of a tetrahedron of sulfide ions. However, since an array of n close-packed ions gives 2n tetrahedral holes, and since there is 1 zinc ion for every sulfide ion, only half of the tetrahedral holes are filled. Last, let us examine a space-filling model of this structure. This model shows us that the sulfide ions are quite large in relation to the zinc ions. As a result, the zinc ions almost fit entirely inside of the tetrahedral holes, with only a small expansion of the sulfide lattice. Let's take a moment to review. The halide or sodium chloride structure can be viewed as a close-packed array of chloride ions with the sodium ions in all of the octahedral holes. The fluoride or calcium fluoride structure can be viewed as a close-packed array of calcium ions with the fluoride ions in all of the tetrahedral holes. Last, the sphalerite or zinc sulfide structure can be viewed as a cubic, close-packed array of sulfide ions with the zinc ions in half of the tetrahedral holes.